In this video I'm going to show you what is said in chapter 0, which is an introduction to computing. And if I can go further, well, let me first of all say this is myself, Dr. Maton, and I'm using the slides of Sepher Naimi, and these are the authors of this specific book, which is the AVR microcontroller and embedded systems using assembly and C. In my course, I am focusing only on C. I'm going to do a little bit of assembly in this specific presentation, but I will be focusing on C then. So if you look at the topics, we're going to look at the internal organization of computers and look at the different parts of a computer. I/O stands for input-output. Memory is where you store data, or it could be instructions also. CPU, which is the central processing unit. Connecting the different parts, in other words, connecting memory to the CPU, connecting I/Os to the CPU, and then also how computers work. First of all, the very important part of any computer or microcontroller is the CPU, the central processing unit, which can be seen as your brain. You will always need to have some sort of a memory where you have to store data that you've worked with, data that you've done calculations on, etc. And there will be I/O devices. There will be input devices like a keyboard or a mouse or a specific sensor. It could be a temperature sensor or a pressure sensor or whatever sensor. And there will always be outputs, which could be an LCD screen, liquid crystal display screen. It could be a printer, hands of a robot. It could be a relay. It could be the closing of a valve, which is also similar to a relay. So yes, those will be the outputs of a computer, and specifically when we talk about microcontrollers. Memory is anything that can be stored and also retained and recall information, like a hard disk drive, a piece of paper. We will talk about in a previous video. I have shown what RAM memory is, what a ROM memory is, etc. And I'll do just a quick over in this presentation also. In a previous video, I've also talked about memory characteristics. The first concept that we looked at is capacity, which is the number of bits that a memory can store, which in this case could be 128 bits or 256 bits, or etc. And the organization, how it's organized. Normally, if it says here 128, it means you've got 128 positions, locations from top to bottom. And by 4, which is an odd number, it's not really like that in real life, but it just shows it's 4 bits, but normally it will be 8 bits. So it will be something by 8, which is the number of bits, which is the standard. And access time just shows you how long it will take to get data from memory, which is also important. What they're showing us here is just a few memory devices. If you look at this specific, this will be RAM chips that you place into a computer. This is a very old hard drive. Nowadays this has been replaced by solid state drives. To younger people, they will not know what this is, but this was called a floppy disk, which was really a floppy type of thing, which is you can bend it. Low storage capacity, and also didn't last long. And then this one here was called a stiffy. And what's interesting, if you look at any programs nowadays, if you talk about saving, you will see this symbol of the stiffy is still used there. Right, let's go to the next slide. So again, in my previous slide, I have spoken a lot about ROM, read-only memory, and RAM memory, so I'll just go over this very quickly. I don't want to elaborate on that because I've got a detailed video on that already. So first of all, let's just look at the ROM, which is read-only memory. Normally you will program this type of memory, and then the majority of times you will rather read from it. It's a type of memory that you cannot really write to too many times, then it will be damaged. I will elaborate again a little bit later in this video. So the first one was that ROM there. A ROM, a mask ROM, is programmed by your IC manufacturer. That was many years ago, so not anymore. You will not find ROM devices anymore. It's programmed by the IC manufacturer, which was very old technology. It was a one-time programmable type of, well, if I go to the previous slide, ROM was also an OTP, which is a one-time programmable device. The next one was a programmable ROM, and it was also a one-time programmable device. The only difference was that you can program it yourself. That was a few years ago. So again, as I've said, this is not, I don't think you will ever get this in the industry anymore. The next type of ROM device was this one, which had a small window in there, and normally you would have programmed this, and after it's programmed you would cover this window so that it doesn't get any sunlight, otherwise it will also be erased. And if you really want to erase it, you remove that the cover or a sticker, whatever you want to call that, remove that, and you shine a certain ultraviolet light on there. I think it was around about for it says here 20 minutes. I think the ones that I've worked with 30 minutes, and then the entire contents of this will be erased. And then you can program it again and keep on reading from it. But as I've said, you cannot program too many times to these type of devices. The next one, which is not old technology, it is actually electrically erasable programmable read-only memory, or EEPROM. And this specific type of memory is still used in the AVR microcontrollers. It's actually embedded. It's part of the memory inside the AVR microcontrollers. It's part of PIC microcontrollers, but you also get EEPROM memory devices that you can, which is also a chip on its own, which you can also use to program it. And once you've programmed it, you can program data on there, or you can actually program instructions on there. On the 8051, there is also a common way to make use of an external EEPROM where you store your program, which can also be read then from EEPROM. It's electrically erased, as I've said. You need a programmer for that, in other words. It is erased instantly, in other words. You can in this specific device, you will be able to erase certain registers or locations. As it says there, each byte can be erased separately, and the disadvantage is it's got limited write cycles of, depending on what you're making use of, 10,000 to 100,000 write cycles, which it looks like it's a lot, but if you really start programming stuff, you can destroy, if you want to program into an EEPROM, you can destroy it within a few seconds and it's gone. So one should always look at the purpose of EEPROM. It's normally to store data in and then to recover that a lot of times, and then only rewrite that data only now and then. The next one, which is flash ROM, also very applicable in today's environment. In microcontrollers, this is where your program, or in microcontrollers, and this is where your program will be programmed in. It's erased in a flash. It's very fast, and the entire device can be erased at once. In other words, instantly everything can be erased. The disadvantage is it's also got limited cycles of 10,000 to 100,000 write cycles. Depending on what you're making use of. So back to semiconductor memories. Let's look at RAM quickly. The first one is static RAM, and this is made of flip-flops or transistors. The advantages: it's faster, no need to refresh. Disadvantage: it's got high power consumption, it's expensive and volatile. What that means is the moment that you remove the power on this specific chip, the data inside, or whatever you had stored inside there, it's gone. That is what volatile means. DRAM, dynamic RAM, it's made of capacitors, so inside it's got capacitors. So the capacitor, let's for instance say it's charged, it will be storing a 1, and if it's discharged, it will be storing a 0. So the advantage, less power consumption, it's cheaper, and you can have a high capacity, storage capacity in it. And the disadvantages are that it's slower, it needs to be refreshed constantly, and it's volatile, meaning as before, RAM, if you remove the power, it's gone, everything will be gone. Whereas ROM devices will be non-volatile. The moment that you remove the power from a ROM device, EEPROM or flash, the data inside there remains there. This is the difference between the two. So that's what volatile, non-volatile means. This RAM normally, as I've said, RAM is a volatile type of device, so it normally loses the data or whatever is inside there once the power is removed. But this is a new type of device which is a non-volatile RAM, meaning if you remove the power, the data will still remain in there, which is, in my opinion, it's actually going to be the newest trend to make use of non-volatile RAM. It's made of SRAM, which means you can actually read and write to it as many times as you like. That's what also makes it you can write to it as many times as you like, which is extremely nice to have. It's battery, it's got an internal sort of battery and control circuitry. The advantages, it's very fast. It's got infinite programming cycles, as I've said. It's got infinite erase cycles, which makes this the best of both worlds. And it's non-volatile, so it keeps the data inside there. Disadvantage at this stage, it is expensive. The internal parts of a CPU, the central processing unit, it should execute instructions. And it should recall the instructions one after the other and execute them. So that is what the CPU will be doing. Now, again, in my previous video or in another video that I've done, I have explained all these pins. Let me just add the rest of them. Here they are. So any memory will always have a ground. There will be a VCC pin. There will be a data bus. There will be an address bus. There will be a write enable. As you can see, this write enable is a low. So this write enable, you can write to the device. So if you make this pin low, you can write to it. There's an output enable. Sometimes it's called read enable. So output enable or read enable, if it's low, then you can read from this device. And the chip select will actually activate the chip. Of course, you cannot have on write enable and output enable two zeros, because if you've got a 0 here there and a 0 there, the device will not know what to do. So if both of them are 1s, it's not a problem, but if both of them are 0s, that will be a problem. So only one of them can be a 0 at one specific moment. And then you will connect your CPU to this memory device. Now, depending on the microcontroller that you use or microprocessor, like the 8051, you will have memories outside. You will also have memories inside, depending on what 8051 series you use. But in the case of the AVR, the ATmega for instance, your memory device and your CPU will be one complete unit inside. Everything will be inside. In other cases, you can have this externally. This memory device of you can be externally and then connected to the CPU, just depending on what microcontroller or microprocessor you're making use of. You can write to memory. So in other words, you can write to this device. If you want to write to this device, you'll have to get the address set up, your chip select, as I've said. You'll have to pull that low, otherwise the device will be deactivated. You'll have to pull that low. Your data must be stable. Your data must definitely be stable. And then if you pull down the write enable line, the data will be written into this device. So this is how the process works. Normally put the data first, then the chip select second. Sorry, the address first, then the chip select, then your data, and then your write into the device. If we look at reading from memory, same story. If you want to read from here, meaning if you read from here, it will go into the CPU on the data bus also. Writing, the arrow is pointing into the device. If you want to read, the arrow will be pointing out of the device. So you can read and write on the data bus. So again, if you want to read from it, get your address bus ready. Enable this device by pulling the chip select or chip enable low. The output enable, which is the read, you must pull that also low, and then your data will actually be read by the CPU. As you can see, as I've said before, the write enable must keep being high, otherwise you're going to have serious problems. So this is high, so the write enable is actually disabled. So connecting IOs to the CPU, this is your CPU. You can connect a mouse to it, a keyboard, a sound card maybe, graphics card, network, etc. You can connect sensors to it to measure different analog values and so forth. So you can see that a CPU should have lots of pins connected to it. Now what we've got here, we've got IOs connected to the CPU. You can connect that using a bus. As I've said, your bus can be, your data bus, control bus can be internal to the microcontroller or microprocessor, or it could also be external depending on the microcontroller that you use. So there's an address bus, there's a data bus, and there are also control lines, the control bus or the write line or the read line. In this specific case, I've got an output IO 0, 1, 2, up to whatever. If you look at what we have here, in this specific case, the CPU was connected additionally to the memory here. On the next slide, you will see that this specific memory device will also be connected to the address and data bus, which is also possible, of course, depending again what you have, what you're making use of. As you can see here, here it is. The memory device is now connected to the address bus, also to the data bus, also to the write enable line, to the read enable line, which is the same as the output enable. And in this specific case, this device is connected to chip select. This device's chip select is connected to ground, which means this device is actually active the whole time, which is not a very healthy condition. And you'll see that in the next slide it is going to be changed, because that is not what it's supposed to be. Depending on your address should actually decide, is it the memory that's been activated, or maybe this IO, or that one, or that one, or that one. And it's possible to make use of electronic circuits or logic circuits, or maybe a decoder to actually decide which device is active just by addressing it on the address bus. As you can see here, with this device actually active here, and if the address, if this address says 0, it will definitely it's actually referring to that location, that address there, but it's also referring to the IO 0 here, which is in conflict. You can't have this thing addressing two separate entities. And this is why there's also, what you could do in this specific case, there's an IO/mem active low. In other words, IO, if you address IOs and you make this line a high, then basically this device could be activated, that one, and that one at the same time, but the address bus will actually decide which data will be activated. If you make the mem, this pin low, which is an active low here, that means this will be all the IOs will be deactivated, and your mem, which is low, is now connected to chip select, which is also low, and the chip select will, and this memory device will now be activated. So this is how you can distinguish between which one to use. And as I said, there are other ways to do it. what the authors of that book and what they show you. They say the logic circuit enables the chip select when the address is between 0 and 15. So in other words, the logic circuit must make sure any address between 0 and 15, because this address is actually from 0 to 15. That's address 16, 17, 18 and whatever. So there's a logic circuit that makes sure that the chip select, any address between 0 and 15, the chip select will be low. And that's actually quite easy with the logic circuit. On the next slides that will be explained. How could we make the logic circuit to work or to get this device active? It says write the address range in binary. So address 0 will be all zeros, and address 15 will be 0, 0, 0, 0, and all ones here. So we can see that the lower nibble, there's a change in the lower nibble from zeros up to all ones. So anything in between will also happen. Address 1, for instance, will be the upper nibble will be zeros, and this last bit will be a 1. That's address 1. But what's important here is to see that the upper nibble does not change. Even if I go from address 0 to address 15, the upper nibble does not change. It says they separate the fixed part of the address. So the fixed section is actually address 4, 5, 6 and 7. So those are the same throughout, as it's shown here. Here you can see this is what we see there. And using an AND, design a logic circuit whose output activates when the fixed address is given to it. So in other words, here's the logic circuit. So if I take a NAND gate with inverters on the inputs, then the chip select will be low. Let's have a look. It will be low here if just before the bubble there's a 1, and there will be a 1 here if all inputs to the NAND gate will be 1s, which means all the inputs before the bubbles or the inverters will be zeros. So any zeros here, if it's zeros here, it means the chip select will be a 0. So any address from address 0, 0 up to address 0F will actually activate chip select to become an output of 0, and this memory device will be activated. It says now design an address decoder for address 300 hex up to 3FF hex. Write the address range down. There it is. This is from address 3. That's your 300 to address 3FF. Yes. So as you can see again, the upper 4 bits remain the same from that address up to that address. 300 to 3FF, it's not changing at all. So you will focus your logic circuit only on those bits. Separate the fixed part of the address, as you can see there it's done, and design the logic circuit. And there's basically here is the logic circuit. Because address 8 and 9, it's already 1, that's a 1, that's a 1. And if 10 and 11, if it's 0 and 0, after the bubble it will become a 1 and a 1. And before this bubble it will be a 1, after the bubble it will be a 0. So any address from 300 up to 3FF hex will basically get this chip select output line to be a 0. An easy way of designing? I don't know. To me this is the easiest way. But basically they're showing basically what we see here is what we have here. So I will not be too concerned about an easy way of designing. This is the way it should be. So inside the CPU there will always be a program counter. This is the program counter sitting here, the PC. Now the PC is actually referring to where the next instruction must be fetched from your memory. That's what the PC, the program counter, is there for. So the program counter supplies where it could be the address of the next instruction. It could also be where to place data. It could also be like that, and I'll show you what I mean by that. Instruction decoder, this is this section sitting here. it will receive from your memory, it will receive an instruction, which is a hex code again, and this instruction decoder will then basically know what to do and execute what to do. ALU, arithmetic logic unit, this is a unit where if I want to, let's say, add two values together, the ALU will do that. If I want to AND two values, the ALU, the arithmetic logic unit, will do that, etc. Any arithmetic logic functions will be executed by the ALU. Registers, in any microcontroller, you will definitely find registers, like in this case A, B, C, D, and depending on the microcontroller, you can have quite a lot of them inside your microcontroller or microprocessor. So what we have here on this specific slide is, again, here's your CPU with the address bus, there's a data bus, there's a write line, there's a read line, and as you can see, it's connected. The write lines is connected throughout to all the IO registers, or sorry, IO addresses, and also it's connected to the memory here. And inside this memory, we actually have, at the address 0, we have got a value of 31 hex. Now, depending on the microcontroller, forget about the 31 hex. It's just inside there's an instruction. That's basically what it means. If you look at this scroll here on the right hand side, it actually means that instruction 31 in this specific case, it's just an example. It means go to address 17, which means it's this one here, and place the content, or collect the content and place it in register A. This is what 31 means. The next one, C4, for this specific example, again, as I've said, don't bother about what it says inside here. The point is there's an instruction. The next one, this instruction C4, means in this case, take the contents of the accumulator, sorry, not accumulator, the contents of A, and place it in register B. So go from here and place it there. It's actually not place it there. It is place it there, but what it means is it's copying it there. So if you put a value in here of 9, you say, but put it in B also, it will copy the contents, meaning it will remain in A and also move to B, or just copy to B. This next instruction, which is instruction number 2, which is 26 hex, it looks like, means go to position number 6, go to this address number 6, or yeah, address number 6, take the content in there, which is 5x, there you can see 5x, and place that in the register A, put it in there. And the next instruction actually says, listen, add A register and B register together. That's what this instruction means then, which is the 81 supposed to be. Add the two together and place the answer in the A register. So we'll see how this executes. And then finally, this at address number 4, it means take the contents of A, which is sitting in A, and go and place it at address number 7. Now address number 7 it's actually this one here, né? So this is what it means. So it's just a very simple program, and what you see here is it's more in line with assembly language. As I've said in my course, I'm not going to do assembly language, but yes, this is what it is. In my case, I will just say, for instance, in C, we will just say add value A and value B, and these things will happen automatically. What you see will happen automatically. But let's go through the process. Let's step through it just to see how it's executed inside a computer or a microcontroller or a microprocessor. How does it work? So you can see the program counter. First of all, it will place on address bus 0. So it actually says it wants to talk to address 0. Now in this specific case, that's address 0 there. This is address 1, 2, 3, 4, 5, 6, 7. And this is 16, 17, 18, and 19. They're not, at this stage, they're not addressing 8, 9, 10, 11, 12, 13, 14, and 15, for instance. But okay, so let's have a look now what's going to happen. As I've said, if ultimately what sits in address 17 will be placed in A. So let's have a look at that. So as you can see, that 31 is now moved into the instruction decoder. Here it is. So the instruction decoder will now basically make sure that the correct address is placed there, and that the correct, in this case, 17, IO 17 will be addressed. And whatever sits on IO 17 will then go through the data bus, and it will go into A eventually. So let's see if that is true. Let me step again. Let's step. As you can see there on the address bus, 17 is placed, which means it's going to address this one here, this IO, this one here. What you see here, if you look closely, you will see that this arrow, it's a poor color to use. This is this yellow, but this arrow is pointing down, meaning the read line is going low. So if the address is 17, it's actually it's pointing to this one. As you pull the read line low, it tells this device, whatever it is, that line will go low, and it will say, okay, whatever you have on this IO, it's coming. IO is an input, output. In this case, it's an input, what's coming from the outside world. Take that value and place it on the data bus, and eventually we're going to put it into the A. So, but let's just step. You'll see on the input of input number 17, there's 9 now. This is coming from the external world, or it could be I'm saying an external world, but it could be another memory maybe. Doesn't really matter. Okay, so this 9 is sitting on IO 17, and as you can see now, it will move in, and it will on the data bus, and it will be placed in A. So as you can see, my first instruction was to go to address 17 and place it in A, and there it happened. Good. Now that was from the first instruction at address 0. Now the address bus is loaded with 1, which means now we want to get the next instruction, which says copy the value of A into the register B. So let's see if that's going to happen. Again, the read line will be pulled low. The instruction, which is C4, will be placed in the instruction decoder. And as you can see, that 9, which is sitting in A, is copied to B. So A copied to B. So the next instruction was executed now. And as you can see now, again, it's placed on the address. It's number 2. So we'll go to instruction number 2. That says go to address number 6, which is this one here, and load that into A, register A. Now in address 6 there's a value of 5 hex. So let's see what's going to happen. So the instruction is first collected from that position, and then the instruction will be executed. This is why the instruction said go to position number 6, address number 6. And this is why the address is now changing to 6, because now it needs to point to that specific position there. And as you can see, that content is moved on the data bus here, and it must be placed in register A. And there it is. It's placed in the register A. So now the next instruction must be fetched again. What is the next instruction? There it's placing on the address bus number 3. So it will go to number 3, which is 81, which is meaning nothing to us, but it means, what it actually means is, if once it's collected it, let's just see how it's collected. There it's collecting the instruction, and that instruction says, but you must add A and B. So this 5 and 9 must be added. And let's execute it. There you can see it's moving 5 and 9 into the ALE. It's adding them, and it's placing the answer in A. So A plus B, 9 plus 5 is 14, and the hex value of 14 is E, and that's why it's being placed into register A. So this is what happened with command or instruction number 3. Now instruction number 4 says, but take the value in A, which is this one here, and go and store it at position number 7. Now position number 7 is this one. At this stage, there's nothing in there, but if there was something in there, the only thing that happens is you're going to replace it. Whatever sits in here, you will replace it if there was something there. So let's get the instruction. Number 4, there it is. It's been placed in here. And if I now carry on again, it will place the address. Remember, it must take the value to address number 7. There it's placing it here. And now it's taking the data, placing it on the data bus, and let me just go back. There it is. It's stored, that value. It was stored in position or register number 7 there. So this in short is how a computer works. We don't need to worry too much about it, but it's good to have an understanding of what's happening inside there. But in C, we are going to, in assembly, you have to work a lot with these registers inside here. You have to basically, although we are going to, in assembly language, it's its own language. It's a language that you use, and at the end of the day, it will convert that to a machine code. But we're going to write it in C, and it will also convert it into the C code. And this movement that we've seen here between the address buses and the memories and the data bus and IOs and etc. inside the CPU, all of that happens just by activating or using the C language. So again, I'm not going to go into too much about this because an instruction has got an opcode and an operand, and the opcode is actually what must it do, and an operand is what, for instance, in the previous example, in this specific case, the opcode was to add 2 values. The operand is which values, etc. So don't be too worried about what we see here. And then just before we stop this video, there are 2 different architectures. Some make use of, let me first of all talk about von Neumann architecture. And as you can see, the CPU, if the CPU wants to get a code, only this, if this data bus is busy, then I can only get the code on the data bus. I cannot at the same time also address the memory. So it's either the code or the data that works at one specific moment. Or the address also. The address can only be for this one, or the address can be for that one. It cannot be simultaneously. And the control bus will either control this memory or control that memory. So yes, they basically do time sharing. In von Neumann architecture, there's some time sharing. Although it's still fast, but there's time sharing. In Harvard architecture, you can see it's different. There's a CPU, and it's got a data bus to the code, and it's got a data bus to the memory. The same with the rest of the buses: data, address, and control bus. So the CPU can actually, in the same clock pulse, get an instruction, and at the same pulse execute a previous instruction. So this is a lot faster, the Harvard architecture. In the case of the AVR or the ATmega, which I'm going to discuss in other videos, they make use of the Harvard architecture, and this is why that microcontroller is extremely fast. Well, this is the end of the slideshow. Let's look out for further videos on this topic. Thank you and stay safe.